Welcome to the 5th video in the Combinatorics series. Let's start by reviewing a few basic ideas in set theory. Here are two sets, A and B. Based on those, can you figure out, or do you know, what these four expressions are equal to? Well, this is A intersection B, where that is the intersection operator, which you could think of as and A intersection B is the set of all elements that are in A and in B. So in this case, that would be the set with just a 3. Again, these bars around sets mean size, which is how many elements are in that set. So in this particular set, that would be only one element, the number 3. So that is not a set, but a number. This is A union B, where that is the union operator, which you could think of as OR. And a number is in A union B if it is either in A or in B. By the way, that is not an exclusive OR. So if it's in both A and B, it is also in this set. So in this situation, that would mean that 3 is in A union B. So A union B is simply 1, 2, 3, 4, 5, and a set does not have repeats, so you only include the 3 once. This, again, is the size of that set, and there are 5 elements in that set, so the size of A union B is 5. Based on just that, we can answer a few questions. We can tackle this problem by formalizing it. So let S be the set of girls that play soccer, and let B be the set of girls that play basketball. And since 27 girls play soccer and 20 girls play basketball, we can say that the size of set S is 27 and the size of set B is 20. And since 14 girls play both sports, the size of S intersection B would be 14. And of course, S intersection B is the set of girls that play soccer and basketball. We can also represent this visually, as a Venn diagram. And again, this implies that there is some intersection. Otherwise, it would be like two completely disjoint circles. But there is an intersection here because there are 14 girls that play both. And you should think about the 3 pieces of this Venn diagram. There are girls that play soccer but not basketball. There are girls that play basketball but not soccer. And there are girls that play soccer and basketball. So this region here represents S intersection B. And we want to count the girls in each of these 3 regions and then add them together. So that's divide and conquer approach. But in this video, I actually want to show you something a little bit different, a different type of strategy. So if you want to find the size of S union B, maybe you want to add the stuff in S and the stuff in B. What are the consequences of doing that? Well, when you add the size of set S, you're counting this region once, the stuff that's in S and not B, and you're also counting that region once, the stuff that's in both S and B. So you've counted that region once and that region once, and you need to count this region once, and so you decide to add the size of B, so you do count that region once because you're trying to count everything in B, but the stuff in B also includes the stuff in S and B, so you're actually counting this region twice now. So you're over-counting, potentially, if there's an intersection, which in this case there is, by adding the size of S and the size of B. So you then need to subtract out the size of S intersection B to get it down to counting it only one time. So you start by including S and B and then excluding S intersection B to correct the count. So because you're including and excluding, this principle is actually called the principle of inclusion-exclusion, or commonly called pi for the principle of inclusion-exclusion. Now let's apply that to this problem, right? So the size of S union B would be the number of girls that play soccer, the number of girls that play basketball, but we overcounted the girls that play both, so we need to subtract it once to make sure we count them only once, and that in this problem is equal to 33. All right, let's try another example. So we can also formalize this problem where we let H be the set of very hairy dogs, let B be the set of big dogs, and we're given a few pieces of information, such as the size of H is 42, or there are 42 very hairy dogs, and the size of B is 30 because there's 30 big dogs, and we're actually given the total number of dogs, which is dogs that are either big or very hairy, which is the size of H union B, which is 50. We can still use the principle of inclusion-exclusion to solve for the number of very hairy and big dogs, because that is just the size of H intersection B, and we have all the other quantities. So we know that H union B is 50, and we know that the size of H is 42, and the size of B is 30, and we need to figure out how many dogs are big and very hairy, which is the size of H intersection B. So just solving this is this 72, so you need to subtract 22 to get 50, so the size of H intersection B is 22, and that is the answer to our question. What if you had 3 sets instead of 2, and you wanted to find the size of the union of the 3 sets? So you want to find the size of A union B union C for some sets A, B, and C, which you can visually represent with this 3-circle Venn diagram. And as you can see, there are 7 clear regions, right? We have this piece, this piece, this piece, this piece, this piece, this piece, and this piece. So things get pretty complicated quickly, and trying to divide and conquer those pieces is not very appetizing. So we should rely on the technique that we've been developing, which is the principle of inclusion-exclusion. So if we want to find the union of A union B union C, we can start by adding the sizes of A, B, and C. So just like we did last time, take a moment to fill out the 7 regions here with how many times they are being counted as a result of doing this. We want each region ultimately to be counted 1 time, right? We want to count everything once, everything in the union. But what happens when we do this? Well, when we add A, or the size of A, we're going to count that piece once, that piece once, that piece once, and that piece once, right? Those are the pieces that are included in A. When we add B, or the size of B rather, you're going to add that piece once, but now you're going to include this piece again, which you don't want to do. You're going to include that piece again, and then that piece you're going to count once, which is fine. All right, and then when we add the size of C, we're going to count this piece once, this piece once, this piece once, as in once more. Now we're actually counting both those pieces twice, and we're going to count this inner piece again, counting it 3 times overall. So what we can see is, although we've counted sort of the stuff that's in A that's not in B or C once, just like we've counted the stuff in C that's not in B or A, and the stuff that's in B that's not in A or C, we've counted that once, but we've counted everything else more than once, and that's not good. We've overcounted by a lot. So specifically the intersections, right? We've overcounted the intersections. So why don't we subtract out each of the pairwise intersections of the 3 sets, because that will lower our count for all of this overcounting in here. So we can subtract the size of A intersection B, we can subtract the size of A intersection C, and subtract the size of B intersection C. And now, what are the consequences that it has on our count? Well, if you subtract A intersection B, we're taking 1 away from this piece and 1 away from this piece, which is good, because we want to bring them down. When we subtract A intersection C, we are subtracting 1 from here, which is good, and we are subtracting 1 again from here, which is good, but then hopefully you see the problem that's about to happen, even though it's a better problem to have than we had before, is when we subtract the size of B intersection C, we're going to correctly subtract 1 from there and make sure that we're counting that once, but we're also going to be subtracting 1 from the supercenter, the piece that is in the intersection of all 3 sets. Now we're counting that piece 0 times, but we want to count it once, so let's add it back. The size of A intersection B intersection C. So now we've counted everything 1 time. Beautiful. Now let's apply it in a problem. We want to count numbers that are not multiples of 2, and not multiples of 3, and not multiples of 5. Well, what would it mean if that were not the case? Well, that would mean that the number is a multiple of 2, or a multiple of 3, or a multiple of 5. So we can actually use complementary counting in this question. The total number of positive integers less than 1,000 is 999. It's the numbers from 1 through 999. So we can start with that and actually subtract out the multiples of 2, 3, or 5. So first, make sure you're absolutely convinced that that does indeed answer our question. And once you are convinced that that's true, we can try to formalize the situation. So let A sub k be the set of positive integers less than 1,000 that are multiples of k. then we could represent the set of multiples of 2, 3, or 5 as the union of A2, A3, and A5. And the number of such multiples is the size of that set. So the answer to the question is 999 minus the size of A2 union A3 union A5. So now that we have that, we can sort of zoom into the subproblem of evaluating, well, what is this equal to? And luckily we have the principle of inclusion-exclusion for that. Okay, I'll give you a moment to try to do this on your own. Okay, so how do we find the size of A sub 2? How many positive integers less than 1,000 are there that are divisible by 2? Well, the first one would be the number 2, which is, in some sense, you can think of it as 1 times 2. And the last number is going to be 998, right? That's the last number that is below 1,000 and a multiple of 2. So that is 499 times 2. So we're going from 1 times 2 to 2 times 2 to 3 times 2 to 4 times 2 all the way to 499 times 2, which implies that there's 499 multiples of 2. So the size of A sub 2 is simply 499. And we can use the same process for pretty much all of these. So A sub 3 is going to be the numbers that are less than 1,000 that are multiples of 3. So how many of those are there? Well, you're going to go from 3, which is 1 times 3, to 999, which is 333 times 3. So that means that A sub 3 is 333. A sub 5 is, well, that's going to go from 1 times 5, that's the first multiple of 5, all the way to 995, which is not 199 times 5. So that's 199 different numbers over here. Okay, and then now it gets interesting. So what does it mean for a number to be a multiple of 2 and a multiple of 3? Well, that means it's a multiple of 2 times 3, or a multiple of 6. Okay, well, how many multiples of 6 are there? Well, we're going to go from 6, which is 1 times 6, all the way to the last multiple of 6, which would be 996, which is 166 times 6. So there's 166 of these. Okay, and then for 2 and 5, well, now we're counting multiples of 10, so we're going to go from 10, which is 1 times 10, all the way to 990, which is 99 times 10, so that's 99 over here. And then we can apply the same thing here, and I promise you're going to get 66. And then now you can think about this. So A sub 2 intersection A sub 3 intersection, that's multiples of 2 times 3 times 5, which is actually multiples of 30. And so for multiples of 30, well, you're going to go from 30, which is 1 times 30, to 990, which is 33 times 30. So that means that this is 33. And if you do all this, so you add these 3 numbers and you subtract these 3 numbers and then you add that number, you get 733. But we need to do 999 minus that, so the answer to the question is 266. Next. We can do this the same way we did the last question, starting by complementary counting. So we want to count the number of distributions where everyone gets something, or each of your 3 friends gets at least 1 gift. Instead, we can count the total number of distributions and subtract out the bad ones, right? But what does a bad one mean in this context? What does it mean for it not to be the case that everyone gets something? Well, that would imply then that someone got nothing, right? At least one person got nothing. So instead, we can figure out the total number of distributions and subtract out the number of distributions where someone gets nothing, at least one person. All right, well, how do we think about this second piece here, the number of distributions where someone gets nothing? Well, we can use the language of sets. So let's say that your friends are friend 1, friend 2, and friend 3. And let's define A sub k as the set of distributions where friend k gets nothing. So A sub 2 is the set of all distributions where friend 2 gets nothing. Okay? It doesn't say anything about what friend 1 or friend 3 get, it's just that friend 2 gets nothing. That's what A sub 2 is about. So if we want to think about all of the distributions where someone gets nothing, that corresponds to the set A1 union A2 union A3. So we have 2 things to figure out here, the total number of distributions and then the size of A1 union A2 union A3. Well, what's the total number of distributions? Well, if you have 8 distinct objects that you want to give out to 3 distinct people, Well, you can go object by object, and for each object you have 3 choices, and regardless of which friend you give it to, there are always going to be 3 choices for every object that you get to. So using the multiplication rule, the total number of distributions is simply 3 to the power 8. Okay, now this one, we can just use the principle of inclusion-exclusion, right? So here's the formula, and now we just need to evaluate each term. So what is the size of A1? How many distributions are there where friend 1 gets nothing? Well, if friend 1 gets nothing, that means for each of the 8 gifts, there are only 2 options, the other 2 friends, right? So by that logic, there should be 2 to the 8 distributions where friend 1 gets nothing, and there should be the same amount of distributions where friend 2 gets nothing by symmetry, and the same for friend 3. So we can just multiply this by 3 instead of adding it together 3 times. And now, okay, we want to subtract out the intersection. So what does A1 intersect A2 mean in context? It means that friend 1 and friend 2 get nothing. Well, how many distributions satisfy that? That would mean everything goes to friend 3, and that's 1 distribution. So minus 1 for that, there's only 1 distribution in that set. And similarly, there's going to be 1 distribution in that set. There's only, for 1 and 3 to get nothing, you need to give everything to 2. That's 1 distribution. And then same thing for A1 intersect A3, or A2 intersect A3. Now, for this last piece, A1 intersect A2 intersect A3, we need to add that back. So how many distributions are in that? When is it the case that person 1, person 2, and person 3 get nothing? Well, that can't happen, right? Because you have to give each gift to somebody. So there's 0 outcomes there. So the answer to the question is simply 3 to the 8th minus 3 times 2 to the 8th, and that's minus 3, but you're subtracting it, so it's going to end up being positive 3. So this is the answer, and we can move on. What if we wanted to find the size of the union of 4 sets, or 5 sets, or 6 sets, or 7 sets? Well, the formula is a little bit complicated for that, but interestingly, the structure of it is pretty much the same as what we've been doing already. So consider the size of the union of n sets A1 through AN. You want to start by including the sizes of each of the sets individually, which, by the way, that's going to give you n terms. And then you want to exclude all of the sizes of the pairwise intersections, because we would have been overcounting all of them by this first line. And how many of these terms are there? Well, each of these terms corresponds to some 2 subsets in no particular order, right? I could have written this as A2 intersect A1, for example. So each of these terms is basically corresponds to a subset of size 2 from the elements A1 through AN. So there are, sort of by definition, n choose 2 of those terms. And then we want to include the sizes of the triple intersections, because we would have over-subtracted from this line. And how many of these terms are there? Well, there's n choose 3 of these terms. And then we want to exclude the quadruple intersections, and there are n choose 4 of those terms. And we want to do that all the way to the end, where we're thinking about the intersection of all n sets. And to decide whether to include that or exclude that is going to depend on the evenness or oddness of n. And so the way of handling that is with this -1 to the power n plus 1 coefficient. And how many of these terms are there? Well, that would just be, well, we want n of the sets, so that's n choose n, which of course is simply just 1 term like this. Now, we're not going to prove this in this video, we're going to prove this in a later video, but we can certainly use this to answer questions. So we can use the complement principle. In order to find the number of distributions where nobody gets their own exam, we can instead find the total number of distributions and subtract out the distributions where someone gets their own exam. So let A1 be the set of distributions where student 1 specifically gets back their own exam. And similarly, we can define A2, A3, A4, and A5, and the set of distributions where someone, at least one person, gets back their own exam is the union of those 5 sets. So we want to find the total number of distributions minus the size of that union. So what is the total number of ways I can give back the 5 exams? Well, that's just how many ways can I order 5 exams, right, amongst the 5 students. So that would be just 5 factorial. Okay, great, that's easy. This other one, we can use the principle of inclusion-exclusion. So we need to find the size of A1. How many distributions are possible such that student 1 receives their own exam? Well, if you give student 1 their own exam, there's 4 factorial ways of giving out the remaining exams. So that is going to have 4 factorial distributions in it. And by the way, by symmetry, A2, A3, A4, and A5 should all have the same number of distributions in it. So we can just say 5 times 4 factorial. And now we need to subtract out all of the pairwise intersections. But just like the singleton sets, each of the pairwise intersections is also going to have the same number of distributions in it. And let's just think through it once. So A1 intersection A2 is the distributions where 1 and 2, they both get back their own exams. And that leaves 3 factorial ways of giving out the remaining exams. And that would be true regardless of which 2 you chose here. It would be always be 3 factorial ways of giving out the remaining exams. So for each of the 5 choose 2 pairwise intersections that you need to subtract, each of them is going to have 3 factorial distributions. And then we need to add back the triples, but again, all of them are going to have the same number. So 5 choose 3, there are going to be 5 choose 3 such triple intersections, and each of them is going to have the same number. So let's see what that is. So A1 intersect A2 intersect A3, that means 1, 2, and 3 all get their own exams back. So there's 2 factorial ways of giving out the remaining 2 exams to 4 and 5. So that's 2 factorial. And then the pattern is going to continue. You're going to get 5 choose 4 times 1 factorial. And then finally, you need to add back the 1 intersection of all of them. And what is that here? So how many ways can all of them receive their own exam? Well, that would be just one way. They all get their own exam back, so plus 1, which if you do it out is equal to 76. And so the answer to the question is 5 factorial minus 76, or 120 minus 76, or 44. Now you can do your homework.